Do you ever wonder what goes into the creation of a smartphone like the one in your pocket? I'm sure you've heard a lot of elements in some components: aluminum, lithium, sulfur, and even iron. But how about some of the lesser known elements? Today, let's talk about one of those elements: indium. First, let's talk about atoms. Atoms are formed by three subatomic particles combining. A neutron is a neutral charged subatomic particle which combines with protons, which are positively charged, and negatively charged electrons to form atoms. Isotopes are different versions of elements with different atomic weights and neutron counts. There is only one stable isotope of indium, indium-113, with 41 unstable isotopes. This stable isotope is formed by the beta-minus decay of cadmium-113. Beta-minus decay is a form of decay in which a neutron transforms into a proton, forming a new atom of the same weight but different proton count, thus creating a new element. Indium is created through both R and S processes of neutron capture, with S process being the more common source. S process, or slow process neutron capture, is when atomic nuclei slowly gain neutrons over extensive periods of time. If the formed isotopes are unstable, they are able to undergo beta-minus decay to stabilize. R process, or rapid process neutron capture, occurs when neutron stars merge and nuclei break down, and the rapid reformation of heavy molecules also occurs. This process normally occurs way too fast for beta decay to occur and stabilize these atoms. Approximately 5 billion years ago, our solar system was not much more than a vast field of stardust, with no objects visible without the aid of a microscope, until a nearby supernova explodes, releasing vast amounts of energy in the form of shock waves into the dust field, making these microscopically small objects start to rotate counterclockwise and flatten into a disk. At the center of this disk, these small objects begin to crash together, and when these objects made contact with each other, they stuck, forming larger and larger objects which combined into the star we now know as the Sun. The Sun made elements as heavy as iron that eventually were able to escape the gravitational field and combine with other escapees to form the other masses in our solar system: planets, comets, and asteroids. While the Earth was being formed, the pressure exerted on its interior became so great that the heavy metals like iron and nickel inside of the Earth began to liquidize, much like how clenching an ice cube in your fist will make it melt. This created the core of the Earth. Over time, other heavy metals began to sink in the crust, forming a semi-liquid mantle which resides under the Earth's crust. The most common charge of indium is +3, with an ionic radius of 80 picometers. To put into perspective just how small this is, the radius of the average human hair is about 75 million picometers. But this charge means for your average atom of indium, it will need to lose 3 electrons in order to have a stable octet. Within the Earth, indium has an equal concentration among the upper and lower continental crust, so it is just as likely to be found in sedimentary rocks like sandstone as it is to be found in magma from a volcano. Indium is classified as a chalcophile or sulfur-loving element. This means that indium is most commonly found in sulfur-based minerals, such as fluorite, a zinc sulfide mineral with the chemical form ZnS. In this case, indium will substitute for zinc to bond with sulfur. The comparison of the radius of indium and sphalerite compared to the sulfur ion can help determine the shape that the lattice forms during formation. And for this, we have a coordination number of 6, with an octahedral coordination or diamond-shaped crystal lattice. Did you know that the element powering your smartphone's touchscreen isn't even mined directly? Indium isn't mined from its own deposits. Instead, it's produced as a minor byproduct, mainly during the mining and processing of zinc. So when miners extract zinc from the earth, usually in places like China, Canada, Peru, and Bolivia, a small amount of indium comes along for the ride. Once the raw materials are out of the ground, indium is separated through a chemical process called roast-leach-electrowining, or RLE. This involves roasting the ore, leaching out metals with strong acid, and then using electricity to pull out the indium. Indium can also be recovered from copper and lead refineries. But the story isn't just about chemistry, it's also about people. According to the U.S. Department of Labor, zinc is used to make indium in South Korea, and it has been linked to mines in Bolivia that exploit child labor, with kids as young as 13 working in dangerous underground conditions. Mining expansions can also lead to the forced relocation of indigenous communities, along with serious environmental damage. Despite these issues, indium is essential to our devices. In your smartphone, it is used in indium tin oxide, a transparent material that functions as an electrode in touchscreens. Its excellent conductivity and transparency make it ideal for this role. And when the phones are recycled, yes, indium can indeed be recovered. The process involves leaching disintegrated screens using sulfuric acid, allowing some of that precious indium to be reused instead of lost. From hidden byproduct to high-tech essential, indium's story is more complex and more human than it first appears. Think about that the next time you tap your screen.